Okay, so before we talk about what is beyond this course, I want to ask some final question about MaxFlow. Okay. I didn't kind of finish this last time. So just to recap what we had, like we know MaxFlow, like we get approximate MaxFlow on DAX with quite a simple algorithm using push reliable in n square time. And MaxFlow on Expander, you can use push reliable too. And just to make sure that you really know this, this is in the last optional homework that you can have a look how to do it. It's just analyzing push reliable. And here you get nonlinear time, okay? Not even n square, is nonlinear time. So the natural question is, can we kind of push forward this approach, the push reliable, the thing that is quite simple, to be nonlinear time, okay? But you see that the bottleneck is already on the DAG. Okay? Like we show some way to kind of generalize algorithm on DAX and on Expander, combine them somehow together using Expander hierarchy and make it work in general graph. But even on a DAG, what we learn is it takes n squared time. Okay? So it turns out that this is a key bottleneck, how to do this on the DAG, how to solve MaxFlow on a DAG. And in fact, there is a formal reduction showing that if you can solve approximate MaxFlow on DAGs, then you can actually get exact MaxFlow on general graph. This is in a paper that I will publish soon, but like this is like a formal bottleneck. Yeah. If you can get something on DAX, then you're good. So here's a question, right? Just can you show some simple combinatorial algorithm that takes almost linear time to compute approximate MaxFlow on DAX? If you can do this, it will just give a combinatorial algorithm for exact MaxFlow. So that's basically kind of a really nice question that I think is good to think about. I believe that maybe in 5 years or sooner, there should be like maybe some easy to understand and simple nonlinear time algorithm for MaxFlow. So yeah, like just again, I want to know that there is a known algorithm with almost linear time for MaxFlow, as I mentioned. But the algorithm that we know right now, it uses something called intermediate point method. This is like a generic method for solving linear program. And combine this kind of iterative optimization method with dynamic graph data structure. So it's like a really cool result. And but the thing that one can say the drawback about this is that intermediate point method, it kind of maintains some numerics, some numerical number, like some numerical number that you have in the algorithm, but it doesn't have a clear combinatorial interpretation of what's going on. Okay, like sometimes what we want is like understanding. We don't want just fast algorithm. We want to understand what's going on. So this is not clear to me, at least, what's going on in this algorithm. And also the dynamic data structure that is used in this almost linear time algorithm is quite complicated. So I think we can still hope, though, that that should be easy to understand and simple to implement nonlinear time algorithm. Like this is like something that maybe the whole area can push forward to that direction. I think that's a good thing. Okay, so that's basically about MaxFlow. Okay? That we spend some time on this. Now, let me tell you about what's beyond this course. Yeah. Okay. So there are more graph decomposition out there. Okay? So so far, most of the graph decomposition algorithm that we develop is for something called flow problem. What is a flow problem? It's like something like MaxFlow, multi-commodity flow, tree packing, that kind of thing. And also shortest path. Like shortest path is like a flow problem because you kind of want to find a path from something to something. It's like routing something to something, right? Yeah. Okay. What's going on? Okay. Yeah. So shortest path and MaxFlow are kind of quite different. Like they are both flow problem, but MaxFlow is kind of you maximize throughput. You maximize, like you find many paths. The path can be long, but you want many paths. For shortest path, you kind of just want one path that is as short as possible. So like one is maximizing throughput. Here is kind of minimizing dilation, like the time. Okay? So it's kind of, it's optimized different things. Yeah. And you can ask about something that optimizes both, like mean cost flow. Mean cost flow is like the problem that you try to maximize throughput, but you also want to minimize the delay on each path. The path should be short, but you want many paths, like that. Yeah. Okay. So all of these are flow problems, and it kind of encompasses so many problems in TCS. Yeah. And what we learn, we kind of learn this thing. Okay. We learn expanded decomposition that is useful for MaxFlow stuff. Yeah. But there are another part of the graph decomposition that is useful for distance. Okay. And it's actually developed even earlier. Like there are like by now like maybe hundreds of papers related to this. What we learn is more recent. Yeah. And there are like this thing that is just developed like in the last few years. It's kind of something called length constraint expanded decomposition that is useful for all these things. Okay. So what I'm gonna tell you is, I'm gonna tell you what is this. We want to know how to construct it, how to use it, but at least you will know what it is. Okay. All right. Okay. So we know what is flow, but like in the setting where we care about both capacity and length, imagine you have a graph. Okay. You have a graph. Let's say it's undirected. And now let's say that it has unit capacity for simplicity, but each edge has length. Okay, it has some length, like this has length 1, this has length 2, 2, 2, something like that. Okay. And now multi-commodity flow is just like before, it's just how like you assign number to path, like before, right? You can have this flow of value 1, this flow of value 0.5, of another path here of value 1. And the congestion is just like before, but now, okay, yeah. So to be precise, here the congestion is 1.5 because of what? Because this flow has value 0.5, this flow has value 1, but the capacity on this edge is just 1. And now we can talk about length of the flow, not just congestion only. We talk about length of the flow. And the length of the flow is just maximum total length of in every flow path. Okay. So, like the length of this guy is what? Is 6. The green one is 6. The length of the blue path is 1. The length of the pink path is 7. So it means that the length of this flow is 7. Just maximum length. Okay, so that's just, given the flow, you can define both congestion and length, and we will care about both. Okay, and length constraint demand is like a demand that is constrained by length. Just similar to demand that is constrained by connected component that we have kind of talked about. Now, it's the demand that is constrained by length. What I mean is that I said that demand D is H length constraint. If you only want to send flow, like the demand is more than 0, only between pairs that are like at most H away from each other. Okay. Like previous class, we talked about component constraint demand. So only try to send flow between the same connected component. Here, only try to send flow between pairs that are close to each other. Okay. So like here, D is maybe like 1 respecting, because this sum is at most 1, this is at most 1. But it only try to send flow between the guys that are within like length H. Okay. I don't want to send flow between this guy to this guy, for example. Like the guys that are far away, I don't want to do that. So that's length constraint demand. And length constraint demand is easier to route. Why? Because it's constrained. Like there are like less things you want to route. Let me give you some example. Suppose that the graph is a path. And let's say that the node weighting that you want to route is like just all 1. So if the graph is just a path, then A is not routable with congestion less than n, right? Because, for example, if this graph is a path, if I want to route from the left to the right, the congestion here will be like really a lot. Okay, so A is not routable with congestion like less than n, much less than n. But if I say that, but actually, when I look at okay, but A actually is length constraint routable. What I mean here is like there exists flow of length at most 4 that route any A respecting demand. Sorry. There is, I should say that, maybe let me define like A is, let me define what I mean by the node weighting is routable. A is H length constraint routable with congestion kappa and length L. Yeah. If for any demand, for any H length constraint demand, D that respecting A, D is routable, like there exists flow F routing D with congestion kappa and length L. right? So it's just the same thing, except that when I say that it's length constraint routable, I just care about length constraint demand. Right? Just this kind of same notation, but I just have this thing. Yeah. Okay. And now you can see that like A now is actually length constraint routable with length 4 and congestion 4. The congestion now reduced to just something small. Why is that? Because you see that if I want to route between only like guys that are close to each other, right? The worst thing that like the route, like let's look at one edge, right? The worst thing I can do might be just like some like the guy that are like length flow away from each other. It can just route maybe at most 4 units from this side to this side. So the congestion here is like at most 4, because there are not too many pairs that are like close to each other. Okay. Does this make sense? Okay. Yeah. So when you only look at length constraint demand, it turns out that you can get lower congestion. Okay. Okay. Now when we talk about the node weighting can be routable, is routable with low congestion and length, now we can talk about length constraint expansion. So okay. So recall that when I said the graph is just expander, it just means that the node weighting is routable with low congestion. But now we're going to care both about congestion and length. Okay. So how should we define this? Okay. Yeah. So I just I say that G is hash. This is parameter for length. And S is for some slack. Okay. G is HS length constraint for expander if the following is true. If the degree node weighting is H length constraint routable with length HS with low congestion. So what does it say? It means that given any demand between pairs that are like H far away, like demand only between the close guy, now I can route with flow that are short too. It's almost as short as H, but I allow some slack. Like the flow can be of length now HS. Think of S maybe 2 or 10, right? Okay. So any demand between guys that are like H away from each other, I can route all of that demand with flow that are short, almost as short as H, and the congestion is also small. So you see, this is like the notion that care about both congestion and length, right? Okay. Okay. And A is HS length constraint for expanding if A is H length constraint routable with length HS. Anything between A that are close to each other, you can route between A with length almost as short as H, and congestion like 1/5. Okay, here is a quiz. So think of H as like something, both H and S as something like constant for now, and think of phi as a constant too. Okay. Which one is a length constraint expander? Which one is not? What like is a clique a length constant expander? Yes or no? Yeah, it should be. If it doesn't, then there's something wrong with the definition. Yeah. Okay. Yeah. This is it. Yeah. This is good. How about this? What about the path? Who think it is? Who think it's not?
Would it depend on the length of the path? Or?
Yeah, think of the path here is of length n, really big.
Okay.
But here h is like tiny. Okay.
It feels like as long as h is constant, then it should be, because that we'll get congestion proportional to h.
Yeah. Good intuition. Yeah. So a path actually is. Why? Because just like what we have seen, right? When you have a path and you only look at length constant demand, like h length constant demand, like there can be only demand between closed skies. Okay? So the worst thing the worst congestion you can cause is at most h in a path. Okay, and the congestion is at most h, but like h is a constant. So like you can draw with congestion like constant. So it's like a phi expanding.
Could it be h squared or?
It will not be h squared. Why? Like I claim that like the worst thing that you can do is just really kind of like this thing. Yeah. That's kind of, you have h pairs here.
If n is smaller than h, then it is not an expander, right?
If n is smaller than h, why again? I'm not sure.
I mean, I'm just so like if the length end of the path is very small, wouldn't it just be the case of a normal expander?
Yeah. If n is less than h,
or would it still be a?
Right. Okay. Another way to say is that if h is as big as n,
Yeah.
then it's not an expander,
Yeah.
because the congestion is like as big as n.
Yeah.
Yeah. But here the point is I only focus on small h.
Yeah.
So the congestion is like constant. Yeah. This is like less than 1/5. If you set phi to be like a small enough.
Yeah.
Okay. What about this one? Is it or is it not? Yeah. Who think it is? Who think it's not?
Oh, 3. No, 3 isn't.
Yeah. Okay, good. You're right. Yeah. It's not. Yeah.
If one of the peaks is like constant size, is it?
If one of a clique is a constant size, then it is.
Okay.
But if one of a clique, if these two cliques are actually both are big, then now like you can have short demand between the two cliques. But now the congestion here is big. So this is not. What about this? These are like a clique of size n, and there's like a path here of length n too. Is it an expander, like length constant expander or not? Who think it is? Who think not?
Because we can have like congestion n on like the start of the edges along the start of the path.
Yeah, you said that maybe the congestion is n on this guy. Okay.
like right at the start, because we can be like have a demand from like the entire clique to like the second node on the path or something.
So you said, okay, maybe all this guy want to send to this guy. But then it would not respect this guy. This guy have degree only 2.
Okay.
So like only 2 units can be sent to this guy. So that's not the example. Is there actually an example? Yeah.
Actually, never mind.
So yeah, like it turns out that this is an expander. Yeah, this is a length constant expander. The way that you should think about this is actually this. Just focus yourself on like some small neighborhood, right? Because yeah, basically, so let me tell you first why this is an expander. Because okay, this guy is big. But from the local view of this guy, it just looks like a click and here, right? It will never send any flow to somewhere further than this part, because otherwise it will not be a length constant demand. Okay? From the local view of this click, the graph looks like this. And when the graph is like a click with some small length path, constant length path, this is a length constant expander. So the way to view, to kind of see quickly if the graph is a length constant expander is just kind of look at the graph, look at any like small neighborhood of length h, and determine if that neighborhood you can route anything there. With low congestion and low length, right? And here the neighborhood here looks like the neighborhood here looks like a click with some small path. The neighborhood here looks like just a path. So every place it looks like an expander. So that's when this is like, that's why like this is length constant expander. Okay. Okay. Good. And now so now we know what is length constant expander. I will try to now tell you, like I wanted to define length constraint expanded decomposition. But to do that, I need to define a cut. Okay. Length constraint, like expanded decomposition is like a cut that you cut and then you get a components of expanders. Now, what is length constraint cuts? Length constraint cut is not a subset of edges anymore, but it's like a fractional value that you put into edges. So a cut C is like a mapping from each edge to numbers, fractional value. H length constraint cut map each edge to number from 0 or 1 over h, 2 over h, up to 1. It's like a fractional value. And the length, now the way that you should think of this cut is like, this thing is kind of how you would increase, it's like how you increase the length in the graph. So what I mean is that if you consider G as a cutting C, okay, just think of this notation as G as a cutting C. Okay. Now, G after cutting C is like is defined like this. It's a graph where the length of some edge is increased. So the length of HE in G minus C is just the length of an edge. But you increase it by H times CE. So if CE is 1 over h, then this is just 1. But if C is 1, like CE is 1, if this is 1, then this thing would be h. Okay. So length constraint cut is like length in how much you increase the length, ranging from 1 to h. Why do we call it cut? The intuition is this. We call it a cut because if you think of CE equals 1, it's like you cut this edge completely. Why? Because when C is 1, E will be completely useless for length h flow, right? Like if you want to consider like flow that is like of length at most h, now this edge has length much more than h already, so you will never use it. It's almost you cut it from the graph. Make sense? Like, so yeah, similar to like, so like how much you increase the length, it becomes more and more useless in the graph when you care about length. Okay. So is this clear? Okay. So this is what length constraint cut is, and the cut size is just a sum over all CE. Yeah, this is just a cut size. Okay. And now I can define what is expanded decomposition in the length constraint setting. So you have a graph, some node weighting A, some parameter phi. Okay. What expanded decomposition is just it will return you a cut. It's a length constraint cut. It's HS length constraint cut. Such that A is HS length constraint phi expanding after you cut it. And the size of the cut, you should think of as maybe like 1 million for now. Okay, some slack, but yeah. So that this thing you don't need to care too much. Yeah. So and the cut size is like phi times A. Like if you don't care about this, this is just like before, right? Phi log n times A, the cut size. But here, if the smaller the slack, you have some more overhead here. Okay. So what does it say here? It says that, like maybe I should say that given an parameter h and s, yeah, then there is a length constraint cut such that after you cut, now like A is expanding after cutting, and the size of the cut is small compared to the node weighting. Okay. Like think like this. You have some node weighting, right? This node weighting might not be expanding. Like these are the things that are close to each other. These are the things that are close to each other. But maybe like when you try to send flow between here, there might be like some congestion. And maybe when you try to send flow between here, there are congestion. So like it's not a length constraint expander. When you try to send flow between guys that are short, like that are close to each other, big congestion. So that's not length constraint expander. What this expanded decomposition will do is to say that okay, I'm just gonna increase length I'm gonna increase length somewhere. So that now this group are far away from each other. Right? The length constant demand are now like, these are not close to each other anymore because I increase the length here. Okay. I increase some length, and now like if you look into this neighborhood, now they can send flow with low congestion. This can send flow with low congestion. Okay. And similarly, like this neighborhood can send flow with low congestion. I don't need to send flow between here anymore because they are now already far away from each other. Okay, so expanded decomposition previously is just to separate the graph into components so that every component you can send flow with low congestion. Here, it just in the length constraint setting, you increase length so that every local neighborhood can send flow with low congestion. It's kind of, you replace the notion of connected component, which is kind of clear-cut notion of components, to local neighborhood. Okay. So like, you see that C does not decompose the graph into connected components. I really just increase length. It's not like we don't have the notion of connected component anymore. Like, so that notion that is kind of nice and easy to picture is now gone here. Yeah. But the notation that we develop in this course just extend quite seamlessly to this more general notion. Okay. Question about this notion? Yeah.
I guess like, is there like a way to think about these like gradual length increases? Because like in kind of our non-length constrained notion, we're just like either we're cutting an edge or we're not.
Right.
So how should we, is there like a nice way to think about like doing it gradually?
So first of all, you could just define it to be just 0 and 1.
Mm-hmm.
And then it will be like either you don't increase the length or increase it by like a lot. If you do that, it will work, but now the size of C will be like h more. Because I kind of just really route it to 1. Okay. So the reason that we like make it fractional is just so that we don't need to pay a factor h here.
Okay.
But now, okay, how do we think of this fractional value? You really kind of think of how much you increase the length. You might increase it by 1, by 2, up to hs. Yeah, like just how much you increase. Yeah. Like this is just the same. Like if you look at notion of cuts, there is a notion of fractional cuts too.
Mm-hmm.
And what is fractional cuts? Like even the fractional cuts are just, it's really just like a fractional value such that for any st path, the total value along, okay, let me define what is fractional cuts. Yeah.
So like it's okay to think of this as like a fractional cut.
It's really just fractional cuts. Yeah. Like fractional cuts. Cut C, which is E fractional ST cut is such that the distance with respect to the weight C from S to T is at least 1. So like the notion of fractional cuts really looks like how you increase the length anyway. Right? Why this is like if it's integral cut, it just means like you put 1 here so that like there is no way to like every path from S to T must cross the cut. And fractional cuts is really kind of put some value so that the distance from S to T increase by 1, something like that. And here is like kind of similar idea. Okay. So this is kind of all I want to tell you about length constraint expander. Yeah.
Is there like cut expansion notion for length constraint?
Yes, it's just more cumbersome to define, but you can define it, and there is a like a duality between them too.
Is it still like the gap is still like locked in?
The gap is locked in, yeah. But you see, like the notion of cut expanding is about this fractional cuts. Yeah. If you insist on integral cut, then this gap is like the gap will depend on h. The gap will be like h log n, something like that. This is another reason why we want to define to base our notion on fractional cuts.
I have a follow-up question. Like for the other expanded decompositions, I kind of think of it as like some greedy algorithm where we repeatedly do the sparse cut. Does that also? Can we also do that here with that?
Yeah.
Okay.
You can. It's like look at every neighborhood. If you can send flow, if you cannot send flow within this neighborhood, there is a sparse cut. Increase the length there. Repeat. You're gonna get this thing. Yeah. Okay. Yeah. So this is kind of. I just want you to be aware of this notion because it's useful. Like it has been developed just in the last few years, but now, like there are many applications of length constraint, expanded decomposition, and hierarchy. Like here's like expanded decomposition. I can define a hierarchy just like in our class too. We can define it in a natural way. You can try, but yeah. But now it has like application to distributed algorithms. I will not tell you what this is, but it's kind of something beyond worst case algorithm. Okay. We can get dynamic algorithm for answer distance. We can get fastest multi-commodity flow algorithm that get just constant approximation in close to linear time. It leads to parallel mean cost flow algorithm. Some fault tolerant distance oracle, something, yeah, like a bunch of things. Like just last few years, like I just currently try to explore the power of this, yeah, and some nice application. There's gonna be more for sure. Like this is just the beginning. Yeah. So, yeah. So that's about like length constraint, expanded decomposition. That is about both congestion and length at the same time. Now let me tell you quickly that about distance only graph decomposition. Right. This is like a kind of the old, like more developed area. By now, like hundreds of papers on this. But it turns out that even here, something nice and new is just developed now, soon, like in the last few years. So here's like something that I want to highlight. So the first thing is negative weight shortest path. So when you want to, if you have a graph where every edge is positive, has positive weight, and you want to compute single sort shortest path. Can you do it fast? What's the algorithm to do it fast when the graph has positive weight?
Dijkstra's? Or
Yeah, exactly. Dijkstra will solve that in like m plus n log n times, like super fast. Okay? But what if the graph has negative weights? Okay? The thing that you might have learned in class is Bellman-Ford. Bellman-Ford takes mn time, much more than linear. Okay? But it turns out that and people get stuck on mn for a long time, and then it has been improved in the 90s to m root n. Okay? But a few years ago, Aaron Bernstein, Dhanapol Nanongkai, my advisor, and Christian Wolff-Nielsen, they just developed a really nice and quite simple algorithm to solve this problem in nonlinear time. And how do they do that? They introduce something called low diameter decomposition. It's kind of similar to the thing in your homework, but it's a probabilistic version. And this is what they do is kind of introduce this notion and generalize it to directed graph in a natural way. One can do that. And once they do that, there is a way to make it work. And then you get this. Really nice. Okay. And in just last 2 weeks, we just upload this one where we make it deterministic. And what we do is we define something called path cover, which is kind of a deterministic version of this directed LDD. Yeah. Directed LDD is a probabilistic object by itself. The definition is probabilistic, but there is a way to define. It was not clear even how to define it. What is the correct deterministic counterpart of directed LDD? And here we define it. And once you define it, then it gives you deterministic thing. Yeah. That's quite nice too. And so the point is, there is a kind of a world map of graph decomposition. What we kind of have learned in details and we kind of we know quite a lot is this part, expander part, the graph decomposition for congestion. We learn the thing for one level decomposition, which is expanded decomposition, and hierarchy version, which is SE hierarchy or BSE hierarchy, and it leads to tree-flow specifier. We also learn about the directed version in the last few lectures. Okay. But this is for congestion, right? There's another world of distance. Okay. There is a probabilistic one and deterministic one level or hierarchy for directed or undirected or directed graph. Okay. So this is something that is still going on, and this thing is in 2022. This thing is actually by Gary just last year. This thing is just last 2 weeks. This thing is unpublished. So it's really going on area. And although has been developed since 40 years ago, still it's deep enough to kind of, you can further explore some cool things there. And okay, now this part is missing, and I don't even know what should it be. You can try to define it probabilistic tree flow specifier, but what even are these things? I don't even know what it should be. So maybe like there's something to define here and you might get something better. I don't know. So that's the kind of what's more about graph decomposition that we have learned in this class. But there are much things beyond it. Okay, so now I want to tell you more about like maybe like some, now it's going to be about open problem that might be kind of nice to think about and what is open problem in at the frontier of the area. Okay, so first is in dynamic graph, dynamic graph algorithms. So what is this area? Just again, it's an area where you have a graph, and now you get some updates to the graph. You delete some edge, you insert some edge. But after one update, you don't want to spend linear time to read the whole graph, to recompute things from scratch. We don't want to do that, right? And this is an area such that actually 20 or 30 or something, like by now, they extensively use expander based techniques that we learned actually. Why? Because expander, as we have seen, this is just algorithmic friendly. Flow of algorithm is just easy. Things are easy there. But moreover, it's robust under updates. We have seen that too, quite a bit. And this idea goes a long way. It's like for all kind of dynamic graph problem, like just these two things, it just lead to like 20 or more paper. But yeah, this is the thing that we didn't touch too much about it. Okay. But one thing that I want to highlight is dynamic tree flow specifier. We learned about tree flow specifier. But the dynamic version is like you have a graph. Now you want to maintain tree flow specifier with quality queue. And let's say, and the update is such that you might delete and insert and delete edge. You want to do this in update time queue. So what I showed some years ago is that you can do this actually in dynamics world, where queue is like the quality and the update time is like n to the little one. And you can do it in capacitor graph too with this queue. But it's really important to improve this actually, because if you can get queue to be polylog, it would give at least achieve one of our holy grail, which is it will finally improve this m to the 1 plus little 1 to just m polylog max flow. This is just like kind of the key subroutine that, like the only key subroutine that you need for max flow. So you learn about tree flow specifier. If you can make it dynamic, then it's going to be great. Yeah.
Is there a reason why the quality is the same as update?
Oh, so kind of the running time here is like the running time, which is like kind of, if this is Q and this is Q prime, the running time is like Q times Q prime here. So like it depends on both quality and the update time of this algorithm. So you want both of these to be small. Yeah.
I mean, like, is it known that like this can even exist? Like,
I mean, tree flow specifier with quality queue, polylog that exists.
Oh, okay, yeah, I see.
We have that, right?
Right. Okay. But I guess like so yeah, it's known that like given like a tree flow sparsifier, like if you make like some edit to
The graph.
the graph, like that won't change the tree flow sparsifier by more than like the like
Good.
say
I see
polynomial.
what you mean. Like you asked about like the change complexity, but not the time complexity. Like how much like if we forget about time, how much this three flow specifier need to change.
Right. I mean that would sort of lower bound.
Yeah, exactly.
Right? So,
Yeah.
like, so is it known then that you
No.
can get, okay.
Yeah, that's not known. Yeah.
Is the near linear max flow paper, does that use tree flow sparsifiers or?
There are like several almost linear time max flow by now, but this one is the one that is called almost linear time decremental graph algorithms, the most recent one. This is the one that is just use tree flow specifier. The previous one, it used something called dynamic mean cycle, mean cycle, something different.
Okay, because I guess I was wondering, like, does this mean we have almost linear combinatorial like max flow algorithms and using this?
So, like this one is considered not combinatorial because it used IPM, it used intermediate point method. Yeah. Right. But I would say that using IPM is not such a big deal, really. Is the IPM in that paper is quite simple. It's just hard to interpret what's going on. What is actually the biggest drawback might be that the algorithm here, the dynamic data structure here is quite complicated. That's why like that's the bigger issue to me. Yeah. All right. Good. Another like kind of nice problem is dynamic approximate maximum matching. Let's say you have a graph or even bipartite graph, and you want to maintain like maximum matching, but maybe approximate. And you have edge updates, insert and delete, and like it's easy to get update time, which is something like ON. Okay, ON is easy, known for a long time. I will not tell you how exactly, but you can ask me. But what's open is like, can you do better than ON? And this is kind of a cool area that kind of this thing connects to, like, it turns out that just in the last few years there are some nice connection to sublinear algorithm, and even like just pure math, combinatorics, which is something called Rusa Seremiti graph. You can look up what it is. And also it connects to this Figen complexity. Like it's like just one problem that if you want to look into, you can go deep into like many area. It's like there's some depth into this problem. So that's what I like about it. Another problem that is good is this. This is so simple, and like you might like it. Let's say you have a directed grid like this. There's a 1, 1, n, not n here. You just want to know if there is a path from 1 to n. If every node is active, is there, then obviously there is. But now you can turn on and off each node. I might turn off this guy, turn off this guy, this guy, this guy. Maybe this guy and this guy. Now there is no path. So you can only go through a node that is turned on. Okay. So there is some algorithm that can solve this in ON time. Note that this graph has n square nodes. Okay. So it's still non-trivial because trivially you would need n square time. just to kind of do breadth first search on the whole graph. Here it takes ON update time. Can you do better? That's not known. Yeah.
Is there a reason we only look at the grid instead of like a general?
So yeah, I asked you about the grid because if you can get good algorithm like polylog update time, it will already imply some nice application. It will imply like a optimal algorithm for some geometric problem. And it will lead to like a long-standing barrier for dynamic planar reachability, which is just you have planar graph, not just grid graph. And if you have planar graph with n nodes, people know how to do it, how to get algorithm with root n update time. We don't know how to get better. So it's like a, yeah, but grid is so simple, something should be able to, like, someone should be able to solve it. Yeah. Right. Like, can you just kind of scan, like, the n update time maybe about like kind of scan one row or one column, I don't know, something like that. Can you do better? That's the, okay. So here's something that is cool about another area, parallel graph algorithms. Okay. Just about reachability again. You just ask if there is a path, directed path from S to T. You have a graph, directed graph, is there a path from S to T? So if you use BFS or something simple, well, it takes linear time, linear work or time, but the depth is like n, right? You need to go one step and another step. The depth is big. Now it turns out that by now we know how to do it better. From n, it improved to root n. So that's great. And this is quite recent too, and not too long ago. Question is, can you do it in polylog depth? So this is really important because it really is the major bottleneck for the whole area of graph algorithm, of parallel graph algorithms. Like in many problems in undirected graph, you can achieve something like polylog depth, like shortest path, approximate shortest path, approximate max flow, even like something like advanced like that, or even mean cost flow. In undirected graph, you can do something like this, something close to this, like polylog depth or interleader 1 depth. But once you go to directed graph, now even reachability, let alone shortest path or max flow, we don't know this. Okay? So this is like really major bottleneck of the whole area on how to make directed graph algorithms parallel. And the algorithm are, like most algorithms right now are based on shortcuts. And I want to tell you one nice problem about this. So H-hop shortcuts is this thing, where you have a graph with, let's say, m edges. And I want to add some edge set, E prime, into this graph. Let's say of size close to M2, right? Such that first, if S can reach T in G, now S can reach T in the shortcut graph with small number of hops. Think of H as polylog again. Okay. That's why we call it shortcut. We add something to the graph so that if S can reach T, then you can reach it through shortcut with small number of hops. Like by hops, I mean number of edges, right? But also, if S can reach T in the shortcut graph, then S need to be, S can reach T in G too. Meaning that I never add new connection, right? If S can reach T in after I add short, it's like suppose that if the graphs look like this, S what? Yeah, I mean like if S cannot reach T in the graph, then I cannot add some shortcut from S to T. That's what I mean. Okay. So you see, like it's just shortcut things in the original graph and never add something, but never add something more than that, more than it should be. So the best upper bound, you can actually do this when H is just something like something non-trivial, like n to the 1/3. And there is a lower bound. The best lower bound now is actually by Gary and others. It gives you this. But the thing is that this lower bound, they crucially assume that E prime here never use new vertices. What I mean is that, like, if this is a graph, maybe the graphs look like this. Maybe I add only some edge in, I only add edges where the endpoints are like from the original graph. But if I don't allow adding something like add new node, and then I don't allow adding new node like this. Okay. So it turns out this is crucial because, like, yeah, once you allow adding new nodes, then the lower bound that is all lower bound in the literature breaks down. So it raises the question, if you allow using new vertices, can you still hold for H even equals like at most polylog? So that's just open. Like it's just this is a kind of just math problem. No algorithm. It's still interesting. Yeah. And it turns out to have, it has nice connection to circuit complexity.
The upper bound doesn't use new vertices or?
The upper bound doesn't use new vertices. This one don't use new vertices. Yeah. We just know that the lower bound will break if we use new vertices, but we don't know how to exploit it algorithmically. We don't know how to improve the upper bound using new vertices. Okay, so yeah, this is a kind of nice graph question, no algorithms. But the hope is that if you can find this thing, it's like so far all the algorithm for parallel reachability is based on finding this shortcut and then compute it fast too. And then it leads to this algorithm. Yeah. But now we can just ask if this shortcut exists. Okay. Okay, so next thing that is kind of a hot topic right now, like many people have looked into it recently, is strongly polynomial time algorithm. What do I mean here? So think of the graph where the edge weights or capacity is just huge, like exponentially large. Okay. Strongly polynomial time algorithm is when the time is like poly n completely independent from W. Like W is like the edge weight or length. when you assume, of course, when you assume that an arithmetic operation on the weights, it takes just unit time. Okay. So you kind of like think like you have real numbers and you can add real number in constant time. Example is Dijkstra algorithm. Actually, Dijkstra algorithm, even if the edge weight is like super large, it only uses like comparison. Like if you can compare anything in constant time, the running time is just this. Okay. A weekly polynomial time algorithm is the one where you can spend like log poly n and poly of log w. Okay. Why is that? Because number of w takes something like log w bits. So this is kind of polynomial in the input side. Okay. And many times, like most of the time, we like in many kind of natural case, w is like just poly n. We usually think of that like w is not too crazy big. So in that case, like log w is just kind of negligible. So when you think of w is not too big, then weekly polynomial is okay. The example is actually our Maxflow algorithm. It actually has this kind of running time. Because if you remember, like we just solve approximate Maxflow, and then we solve again in the residual graph. This kind of thing where you kind of need to repeat, like you keep reducing the size of Maxflow by half. Actually, there is like this term, log w there. Okay, but throughout, I usually just think of w as poly n. So this is just log n. Yeah. But people can ask this thing, right? What about strongly polynomial time algorithm? And what's open is this for Maxflow. So weekly polynomial time algorithm, we know almost linear time. But strongly polynomial is still mn. From like Orlin in the 90s or something. Yeah, long time ago, like 30 years. So this is open. And very recently, people know how to break this mn, at least when the capacity is only on vertices. Okay. Negative weight shortest path. If positive weight shortest path is just Dijkstra, you're done. Negative weight shortest path. We know this thing, the one by Aaron, we know this one, Aaron, Danupon, and Christian. But strongly polynomial time is still mn too. But recently, starting by Feynman actually, this gets like the best Fox paper actually. He get like something like m, something like this. Yeah, so break the like 70 years long-standing open barrier, like maybe like last year or two, I don't know, I forget. And now this bar is improved further. How far you can go, okay. So yeah, so why you might think like why you need to ask about strongly polynomial time, assuming that you can spend unit time on number that is exponentially big. That seems strange. Like the model might be a bit strange to you, but the techniques for strongly polynomial algorithm here, usually they are like, when you kind of restrict yourself here, it usually leads you to like novel insights. So yeah, I find that like the techniques here usually are new. So it's quite cool. Yeah.
Do you know how to do like parallel approximate shortest paths in undirected graphs in this strongly polynomial?
There is some recent paper on this, but I forget. Yeah. Okay. So last thing is like a beyond flow algorithm, which beyond flow problem. Like reachability, shortest path, bipartite matching, max flow. Like this kind of encompass a lot of things already, but it's just a special case of mean cost flow algorithm, mean cost flow problem. But there are like a big class of other problem that is kind of beyond, cannot be captured by mean cost flow. The keyword is like some Matroid stuff, but I will not define it. You can read the book or watch some course. I will pick some nice like concrete problem, tell you what is interesting. Yeah. This first thing is mean S-cut and arborescent packing. So let me tell you what it is. Let's say that you have a directed graph. S-cut is like you have S is a node. You have node S, a cut is an S cut if it contains S. Nothing special. Okay. It's an ST cut if it contains S and it doesn't contain T. So now I just say it contains S. Okay. So that's S cut. And the size of the cut is like how many edges going out. I don't count the in edges. I count out edges. Now, S arborescence is a directed tree rooted at S, rooted spanning tree. So, like if this is S and it spans every node, it cannot have like another node like that it doesn't span. Just a tree that spans everything. So it should have another edge like this. Okay, so that's a two natural objects. There is a deep connection between these two, similar to min cut max flow. Since 50 years ago, Edmond shows that maximum disjoint S arborescent packing has the same size as min S cut. So I mean this. What is, if you want to pack, like if you want to find this joint S R3, okay? This is clearly upper bounded by S cut. Because you see, like if you have some if you have a graph, right? And suppose that there is some S cut of size 2. You know that if you want to find like an arborescence, spanning arborescence, each arborescence must cross this guy at least once. So if there is a cut of size 2 here, you can pack at most 2 arborescence. Okay? So this direction is clear. But it turns out that this is equal. Okay? If the minimum S cut, if all the cuts here, maybe like if all the cuts, this is like the mean S cut is 3, then actually you can pack 3 arborescences. So that's pretty cool. Yeah. So compared to flow min cut, it's like this is about min ST cut and min packing disjoint ST path. Like instead of S cut, it's ST cut. And instead of S arborescence packing, it's about ST path packing. It's like kind of instead of packing path, now it's about packing trees. Okay, so this is like a cool thing to know that it exists. But and by the way, like if you have global min cut, like global min cut is just a minimum cut that disconnect some pair S and T. If you can compute min S cut, can you tell me how can you compute global min cut?
Can't you just do that on every node?
You can do a bit better just by 2 calls, actually. Just making 2 calls. Michael?
Just do mean S cut and then reverse all the edge and then call it again.
Right. You compute min S cut and then do it again in the reverse graph. Because, yeah, like, yeah, you think about it? Yeah. Okay. Now what's the state of the art? Well, min S cut, right now the running time is like m times opt. Opt is like a min S cut. Or it has slower running time in capacitated graph. But 2 days ago or something, Kent just showed how to get really good approximation in almost linear time. So like, yeah, very exciting. So this is a state of the art of global min cut too. Like, you can use S cut to solve global min cut. So global min cut is kind of easier, but all known algorithm just solve min S cut. Okay, how about absorption packing? It's kind of worse. For the exact, you can get M polyopt. For capacitated graph, it's super slow actually, like mn square, still like quite slow. Can you hold for almost linear time algorithms? Well, that's the exciting thing to try, yeah, because this is the one of the problem that is not quite captured by min cost flow, and it's captured by matroid intersection that really is kind of interesting and capture many other things. But yeah, this is a kind of something to look at. Right. Okay. Okay, good. I actually have some like 2 or 3 more problems to tell you, but the time is kind of quite limited. Maybe I just continue on Friday. Yeah. And again, like if you tomorrow, like I might just talk for like 10 more minutes on this thing. But if you have any question on class, on the topics in the class or anything, we can just discuss. Yeah. All right. Yeah. Maybe like just let's continue on Friday.